This video is related about group theory, and in this video we will only discuss about tricks and concept of group theory, not proper theory, but tricks which are very useful in a higher mathematical exam, either MSc entrance or PhD. First is order of, as you know what is GLN, and this is defined on a field FQ is equal to q raised to the power n minus 1, q raised to the power n minus q, and so on up to q raised to the power n minus q raised to the power n minus 1. Second is order of SLN, same elements are coming from FQ, is equal to q raised to the power n minus 1, and so on up to q raised to the power n minus q raised to the power n minus 1 divided by q minus 1. In DN, dihedral group, normally we denote it by DN or dihedral N. In script, N is symbol we are using in dihedral group. First is number of elements of order 2. Number of elements of order 2 in DN, because DN is totally depends on N. So if N is even, then number of elements of order 2 is n minus 1. If n is odd, then elements are n. Second is for Dn, if 2 is not equal to d over n, then the number of elements of order d, number of elements of order d in Dn, because we are talking about Dn, dihedral group, is phi d. This is normally we know Euler function, Euler-Toten function, or normally Euler phi function. For example, number of elements of order 2 in D10, because 10 is even, the number of element is by n plus 1. So 10 plus 1 is 11, and number of elements of order 2 in D11 is same as n, means 11. So this is 2 or 3 formula related to Dn. Normally dihedral group of symmetry of regular polygon. Dn, what is Dn? Group of symmetry of regular n polygon, which include rotation and reflection. Rotation and reflection. And also, or order of Dn is equal to 2n. Number of elements of order 2. Next is number of elements of order 2 in J2 cross J2 cross J2 cross J2 4 times. Then this is equal to 16 minus 1 is equal to 2 raised to the power 4 minus 1. So you can write general formula. Why I subtracted 1? Because identity have always order 1. So asked about 2. So 1 is subtracted here because we are calculating number of elements of order 2. So 1 is subtracted. In final result you can find. If this question is related about as G is Z5 cross Z5 cross and so on up to Z5, suppose 100 times, then order of G is 5 raised to the power 100 and number of elements of order 1 is unique as identity. So number of elements of order 5, number of elements of order 5 in G is 5 raised to the power 100 minus 1. Next is Q star means 0 excluded, R star, C star, Q, R, C. These are abelian group but not cyclic. U2 is isomorphic to this group or trivial group, or you can say Z1. U 2 raised to the power R, very important, U 2 raised to the power R and R is greater than 2 is isomorphic to Z2 cross Z2 raised to the power R minus 2. All these are in subscript. And U P raised to the power R and R is not equal to 2, then this is isomorphic to Zp raised to the power R minus P raised to the power R minus 1. This is also in subscript. We know that UMN is isomorphic to UM, UN. If GCD, this is condition, GCD of MN is 1, otherwise we cannot write this. Number of subgroup in Zn is equal to tau n. This tau is number of divisor of n. Number of divisor of n. Suppose in J12 tau 2 raised to the power 2 into 3, and this can be written as tau 2 raised to the power 2 into tau 3 as I wrote above u. So this is a formula you can easily write. This is 3 into 2. How? exponent of this is 2 and exponent is this 1. So you can write easily tau n. Tau n is nothing but product of ki plus 1. And what is I? I is, as here 12, we can write 2 raised to the power 2 into 3. This is our ki, and this is, suppose this is k1 and this is k2. So these are our ki, means powers of prime. Ki is powers of primes. So answer of this one is 6. Number of subgroup in Dn. Number of subgroup in Dn or of Dn is number of divisor n is equal to number of divisor of n plus sum of divisor of n. This can be written as number of divisor as tau n and sum of divisor is sigma n. So explicit formula of tau n, as I already explained, product of ki plus 1, where ki is powers of prime, and sigma n is product of pi raised to the power ki plus 1 minus 1 divided by pi minus 1, where pi are primes, and ki are powers of prime. For example, you can consider 80 as n is 80, 180 sorry, 2 raised to the power 2 into 3 square into 5, then tau 180. Tau 180 is product of powers exceed by 1. So powers are 2, 2 and 1. Now product of these exceed by 1, 2 plus 1 and 1 plus 1. Answer is 3 into 3 into 2 is 18, and sigma n or sigma 180, you can write 180 here, will be 2 raised to the power 3 exceed 1 minus 1 divided by 2 minus 1 into 3 raised to the power 2 minus 1 divided by 3 minus 1 into 5 square minus 1 divided by 5 minus 1. So use these here as pi by exceed 1. So here you can write 3 raised to the power 3 because power is 2 here. If G is abelian, then center of G. If G is abelian, then center of G is denoted by ZG is Z. If G is cyclic, then center of G is again G. Order of center of G ln Fq, as we defined earlier, is equal to q minus 1, and order of SL n over R. When over R, this is equal to 1 or 2 if n is odd, if n is even. Over C, order of this one is equal to n. Let G be a group. Let G be a group and ZG is center of group. If G over ZG or quotient group is cyclic, then this is abelian. Then G is abelian. Identity permutation, or we normally denote this is identity permutation. Of Sn is always even permutation. Even permutation product of two even or odd permutation. Product of two either even or odd permutation. Odd permutation is again even, and product means same. Even product of even is give you even, product of odd give you again even, and product of different is again odd. This is same as sign convention. Sign convention as we study in real system. Plus plus, if plus is denoted by even permutation, then again plus. Negative negative, if negative is denoted by odd, then again positive. If different, then negative means odd. A very important question comes here. The inverse of even permutation means you have to give an even permutation, then its inverse will be either even permutation or odd permutation. Because this is talking about inverse, if sigma is even permutation, then its inverse give you identity, and we know that identity is even, and even only comes when this is restriction, this is even, then this should be even. Otherwise we will obtain different, or its relation will not hold more. This type of question is asked in some exam. Now come to homomorphism or isomorphism. What is homomorphism or isomorphism? Before this, we have some formulas related to permutation. Number of permutation of R cycle. Number of permutation of our cycle in Sn is by n factorial divided by r n minus r factorial. So again, number of elements of order d, number of elements of order d in Sn is by the formula n factorial divided by 1 raised to the power alpha 1, 2 raised to the power alpha 2, and so on, k raised to the power alpha k into factorial of powers alpha 1 factorial, alpha 2 factorial, alpha k factorial, where di, number of I, is selected from partition. Number of I is selected partition of n. Partition of n. When LCM of 1, 2 and k is d. Now come to the point, homomorphism. If a function f from Zm to Zn, then number of homomorphism is by GCD of Mn. Mn are used as in addition modulo or summation of phi d. This is where d is common divisor of Mn. D is common divisor of m and n. If f is a function defined from Zm to Zn Zl with this product, then total number of homomorphism. Take m with n and m with l, means m, n and l. So m with n and m with l means m is distributing over n and l. N and l, as we use distributive property this. So LCM of Mn into LCM of Ml. Remember this point, how to memorize this concept. If f is a function defined from Zm product with Zn to Zk Zl, then m with n and l, and similarly n with k and this is k and l. So total number of homomorphism is by the formula GCD of mk into GCD of ml into GCD of nk into GCD of nl. means GCD of all these subscript. GCD of all subscript. How to take GCD? This is method. Not we are using GCD of K and L. This is not perfect. Now come to the point on to homomorphism. Many times this is asked. If F is from Zm to Zn, then total number of on-to homomorphism. Because as we use on-to from codomain to domain, then we have to check one condition: is n is dividing n m or not. If dividing, then total number of on-to homomorphism exists, otherwise not. Total number of on-to homomorphism exists, and this is equal to phi n. If this is from Z to Zn, then it is number of homomorphism is n, or you can find GCD of n with n is 1. Number of homomorphism from Zn from Zn to Z is by 1. Number of homomorphism is 1. So you should take GCD of this one. GCD of 1 1 is 1. In the previous we used Z to Zn, then number of homomorphism is GCD of n with n, and this is equal to again 1. If we are defining f from Sm to Zn, this is important, Sm to Zn, and m is not equal to 4, then number of homomorphism is by 1 if n is odd, and this is 2 if n is even. Automorphism of Zn is isomorphic to Un. If you want to prove automorphism, then you have to prove 3 things: 1 1, on 2, and homomorphism. This will lead you automorphism. Now, very important, Kochi theorem or theorem, as you pronounce. Let G be a finite group, and a prime P divides order of G. Then there exists a group, or there exists an element. Then there exists an non-identity element, or you can write mathematically as this, such that a raised to the power p is E. Means order of this element is E. Means an element of order P. And this is existence. And condition of existence is P is dividing order of G. Now come to the Silo theorem. Silo third theorem is commonly used in dealing questions of group theory. The number of Silo P subgroup and denoted by n for number and p for p group is equal to number of 1 plus kp and where or such that 1 plus kp should divide order of G and k may be 0, 1, 2 means non-negative integer. If G is G ln fq, if G is G ln fq or S ln fq, S ln fq, then G has q silo subgroup of order, then G has q silo subgroup of order q raised to the power n minus 1 divided by 2. This is sum of first natural number 1 less. This is sum of 1 less sum of first n minus 1 natural number. G has unique. If G has unique P silo subgroup of G, then this is normal. This is normal in G. Very important. Number of non-isomorphic abelian group of order. This is only for order prime factorization of 2 and 3. Number of non-isomorphic abelian group of order 2 raised to the power k1 into 3 raised to the power k2 is pk1 into pk2, where pki is the partition of ki, where pki is partition of ki. Order of zi, qi, ri, zqr are all infinite. But order of Zni, is n square. We know that Lagrange theorem, order of subgroup divide order of group, or element order of an element of group is divide order of group. But converse of Lagrange theorem is not true. Converse of Lagrange theorem is not true. If H and K are finite subgroup of G, if H and K are finite subgroup of G, then order of HK will equal to order of H into order of K divided by order of intersection. Every homomorphic image of abelian or cyclic group is abelian or cyclic. Means every homomorphic image of abelian or cyclic group is abelian or cyclic. Abelian or cyclic. Means homomorphism sent abelian to abelian means commutativity to commutativity or cyclicity to cyclicity. As we discussed dihedral group, so what is the order of symmetric group of n symbol? This is bijection from set to set, set 2 with same set with function composition, and order of Sn is n factorial, and I told you order of Dn is 2n. Now order of n element in direct sum. Order of an element in direct sum. The order of an element in finite direct sum. This direct sum should be finite, otherwise we cannot find. So this is order of, suppose g1 g2 is coming from direct sum. This is element of direct sum. Then this is by LCM of individual order. LCM of order of g1, order of g2. And this g1 g2 are coming from group which are forming direct sum. Now number of element of order k, number of elements of order k in Zn, I think I explain you by phi k. If k divides n, or this is 0 if k not divides n. Now important is, as we define, Zn is a group with addition modulo n. This is abelian group. Every subgroup of abelian group is normal subgroup, and subgroup of abelian group, suppose any abelian group and its subgroup H, then H must be normal subgroup. Now this is formula related to phi n. Phi n can be easily evaluated by this formula. Product of n 1 minus 1 upon pi. These pi are primes. These pi are primes which are dividing n. Total number of subgroup of group I think I already explained this one. Total number of subgroup of Zn, and Zn is abelian if group is abelian, not Zn if group is abelian. Group is abelian and finite. Abelian and finite. Then this is product of pi's plus 1 exit. So these are few related formulas which are using in group theory and very common and well known to clear any exam. So always try to remember these.